Let's start with today's class, which already we've seen the overview of the adiabatic logic gates. Let us concentrate on adiabatic logic gates now. So here we are showing the two different diagrams. That is, this diagram is basically a static CMOS circuit. Here, basically how the adiabatic circuit will be converted from the static CMOS circuit. So here, as I mentioned, this will be like a so here, so there's a small correction as I mentioned. Your pull-up network always it will be connected to the load capacitance, the output. That is, this will be your charging, right? This will be your charging. Then this will be a discharging network. So just by mistake I have given. So this will be pull-up network. This is the pull-up network. The pull-up network is always in a CMOS circuit. It will be PMOS. For pull-down network, it will be NMOS. Here the function is given as F and here is F bar. So in the sense, this will be your F bar in the sense like the F bar is equal to A bar. We have done like AND gate, right, or NAND gate like this. Then if you want to get us F, then what you do? Apply De Morgan's law, which you studied in your LD De Morgan's theorem. Then what will be? F the whole bar is equal to A dot B the whole bar. Then this will become as A double bar plus B double bar. Then this will be A plus B F. That is a function we get. So A B. So this will be A bar B bar. So the input for the transistors for the pull-up network will be A, B. For NMOS, the input will be A bar, B bar. So in this way, we can give. So that is what in the previous class also we have seen. Okay, let us see how to convert the static CMOS circuit to the adiabatic circuit. Now you look into the static CMOS circuit. What you have to do in the sense, the first step is like we need to replace the each and every the pull-up, each pull-up NMOS network and pull down PMOS network. So here I have given the pull-up network. You can take as pull-up network, okay? Pull-up network and pull down network of static CMOS circuit with the TG. So transmission gate. You have to replace with the transmission gate. Then what you need to do? You need to use the expanded pull-up network will drive the load capacitance. Then pulled-up network will drive the complementary of the output. Means the output which will be taken for the pull-up network, like it will drive the true load capacitance. Means there is no complementary output. It will get the output of CF. Then the expanded pull-down network will drive the complementary output load capacitance. Means it will give the output as VFF. That's our F bar. Then we need to replace the fixed power supply by a pulsed power supply. That is nothing but PE. This is what we are going to do. We have seen the example. We realized here our AND and NAND realization. So here we can see this is the normal CMOS. So I can take it like this, okay? X bar, Y bar, this will be X and Y. This is X and Y. So now this is a general 2-input CMOS NAND gate. We connect the BR. Now as I mentioned here, just for our namesake, just we rotated by anti-clockwise or just we rotated left by 90 degree. We rotated. The circuit as will become as in this way X and Y. This will be a X bar, Y bar. Okay. This will be Y. Now what you need to do? Each and every transmission gate, the transistor, the pull-up network and the pull-down network must be connected to, must be replaced by a transmission gate. So now here you can see this will be the output already which you mentioned, the pull up. This will be your pull up, right? So here I may get the output as F. So here you may get the output as F bar. So this will be a output as F will get. But how you can give the inputs, because two transistors are there. We replace the PMOS by NMOS. I hope you remember, right? So now you can see the PMOS transistor's input is what? X and Y. So the PMOS will be X and Y. Then your NMOS will become as X bar. Simple. Okay. Next, similarly for even here also, I will get for this is your pull up network. This portion is nothing but your pull up network portion. This portion is pull down network portion. So here you can see the pull down network. The NMOS is driving X bar. NMOS is driving a X bar. Correct. So when you are changing to transmission gate, NMOS will be a X bar, then PMOS will be a X. So not NMOS. Here PMOS is X, right? PMOS is X. Then NMOS will be X bar. Yes, okay. Then here what will be? We'll get X. NMOS will be here we given as X bar. So NMOS will be X bar. This will be X. Okay, there's a small correction here. Okay, so here we have shown the expression actually here how the pull down network and the pull up network will come. So example here I want to say for NMOS, the equation, the static CMOS equation is actually when you apply the DMOS theorem, F is equal to A plus B. So series will be in the NMOS network, parallel will be in the PMOS network. At the same time, the inputs will be complement each other. So now the function you can see we implemented this normal static CMOS circuit. Already we studied in CMOS well. So just you draw as like that only. So once you draw, so the PMOS, right, that parallel structure, no? So there we given clearly. Now, as in the general structure of adiabatic circuit, you know that the pull-up network and pull-down network, it's a complementary. So this will be your pull-up network. It's a complementary inputs only you have to give into the pull-down network. So here you can see for a PMOS we are given X. Then what will be a meaning? So here for N in the pull-down network, the complementary input you need to give here, because here also it is X in the sense. So here I will give us X bar. Actually it is X bar. It is X bar. Then this will be a X. So let me write. X and X bar, Y and Y bar, then this will be your X bar, this is X, then this will be Y bar, this will be your F, so this will be your this will be your F bar. This is F. Okay. Let us see here, which will provide the output here. This will give the output of AND gate. Here it will give the output of NAND gate actually. So now let us study about the operation. Two cases we'll see for AND gate as well as NAND gate. So now case 1, okay, when the both inputs are X is equal to 0 and Y is equal to 0. When X is equal to 0 and Y is equal to 0, let us apply X is equal to 0 and Y equal to 0, means this will become as X is equal to 0, the X bar will become as 1, then Y is equal to 0, then Y bar will be 1, then X is equal to 0, 1, Y equal to 0, Y bar is 1. Okay, then in this case what will happen? X bar is 1, X equal to 0 means the TG1 is on, correct? So let us write here, channel will be on. So TG1 is on. Next TG2 also is on. You have to assume that initially all these capacitance are not charged. Okay, that is initially it is 0. TG also it is on. TG also is on. At the same time we are applied X equal 0. Then supply, you see that supply we are varying the VA. We are varying. Okay. We are varying from 0 to VDD. When I vary VA to VDD, at the meanwhile time you can see what happened TG3. The TG3, the gate 3 will be off, then TG4 also will be off. So only thing is these two transistors are on, these two transistors, these two TG gates are off. When these two are off, then what about we are varying the VA from 0 to VDD. So then there is no path from this VA to F. There is a path from VA to F bar actually, right? So if it is on in the sense we are giving the range of VDD, this one. So now what will be your output? The F bar is the capacitor will be charged. So the F bar, that is F, right? That is what it will be charged to VDD. Which one? This capacitance, the charge load capacitance charged to VDD. So I'll get it will be F bar is equal to 1. So 0 0 means 1. So at the same time, what will be F? F is 0 actually. F is 0 because there is no path. It is already, as I said initially, the CL was 0. So now we got the output for NAND gate as well as for NOR gate. So as we know that the truth table A, B, F, F bar. So 0 0 0 1 1 0 1 1. So F is nothing but your AND gate, right? So it will be 1. This will be NAND output. That is what here we got. So now okay, let us check for the other condition. Let me go for case 2 condition. Case 2, that is x is equal to 0 and y is equal to 1. So if that is the case, so you are wearing the VA, okay, just to keep it. Now what will happen? X equal to 0, y equal to 1. X equal to 0, y equal to 1. Now you can see x is equal to 0, that is means x bar will become as 1, right? 1. X is equal to 0 only. This will remain same. This remain same. Then y is equal to 1. So y is equal to 1. This will be 1. This will be 0. Then x is equal to 0. X bar will be 1 only. Then x will be y equal to 1. So this is 1. Then this will be 0. Now which and all will be on? You can see that TG1 is on. Correct? This will be on. Then this will be off actually. Right? Then again this will be on. This will be off. Now you can see even this is on, it won't, there is no direct path to discharge from VD. The discharge path is this actually. So this is discharge path or charge or discharge. Okay, same the way here also like this. Charge or discharge. So two ways. But here you can see this TG1 is on. So I will write that TG1 is on. Then TG2 is off. Then TG3 is off. Then TG4 is on. Then what will be your F bar? So F bar will be charged VDD. That is equal to 1. Then what about F? F is 0. So similarly, you have to find out for the other two value also. So similarly, you have to work out for other two cases. Like x is equal to 1 and y equal to 0 and x is equal to 1 and y equal to 1. So you have to check this. Okay, so now this is what we have seen in this. So now from this what we can observe from this in the sense like the very important thing we can make a note. We make an observation from this. The resulting of combination circuits the resulting of the combinational circuits can search fully adiabatic. Fully adiabatic, but their device count will be double. Count is double than conventional CMOS, conventional static CMOS. Now this is the one problem we are facing, and their input capacitance is relatively large. Because of TG. The input capacitance. Now how to it is increased, right? Okay. Now let me say, if the circuit is complexity are large, then how you will construct? Because you have to think about, as I mentioned here early here, you can see, then there's the very important point is that double. Like the result of combination circuit such will be fully adiabatic. There is no doubt in that. It's a fully adiabatic. But if it is fully adiabatic, but the problem is the number of transistors will be more. If the number of transistors gets increased and the input capacitance will be relatively large, the input capacitance is very large, correct? If the input capacitance very large, in the sense, when you talk about your power dissipation, you think about the power dissipation, what will happen? The power dissipation is a combination of what, as we see in something, right? If the input is increased, capacity increases, the power dissipation also will be, but the circuit is fully adiabatic, but the power dissipation will be increases. So what we need to do? So the one idea is that use partially adiabatic, first thing. The second thing is here, as you mentioned, if the circuit is very complex or it's large, then how we are going to construct? If the circuits are very larger, so you need to partition here. The solution is partition a large block of logic into smaller one, and then compose them into implement the original larger functions. So however, the non-adiabatic, rather the fully adiabatic, right? So let us say over the non-adiabatic flow of energy will occur if values are allowed through ripple, values are allowed to ripple, through a chain of cascade. Chain of cascaded adiabatic logic gates. The adiabatic operation is possible. Very important thing is there is something will be there. Like when you never should turn on the transistor, or never you should turn off the transistor during some operation. That is very important with respect to the adiabatic. So now the adiabatic operation is possible only if the inputs of every gates are held stable while the gate is energized. Very important. During this time only we can perform the adiabatic logic. See, this is important note actually. When the adiabatic operation is possible, the adiabatic operation is possible only if the outputs of every gates are held stable while the gate is energized. Okay. Now as I mentioned here, the cascading structure, right? So let us say if the large blocks if you are having, how to make it. So let me take an example. This is the one circuit. Okay, this will nothing but your circuit. It's a large combination circuit. It's very difficult. So now what I'm doing, this will be like, I'll take it in this way. One, I'm broken into smaller logic blocks. So we name it as A, B, C. Okay. So now we need to give as cascading of structures. Okay. So like this. Okay. Then here we have the capacitance. In intermediate stages, as we know that we have capacitance. Right? Then even the output also. This will be your output. Will have the capacitance. Every stage will have the capacitance. This will be your previous stage example, or we can take. Next, this will be our power supply. Now you can check inputs. Okay. This is, I will take it as phi 0. This is, I will take it as phi 1. This I will take phi 2. That is because when you are going for a combinational logic circuits, I cannot, if I break the large combination circuit into smaller pieces, so at that time what we need in the sense, we will have one additional input, that is clock actually. The clock signal I can say. This is the phases. Phi is nothing but a clock signal. So let me say your phi signal is like this. See here you can see in this figure all same. Okay, this all are same. This will be your 50, 51, 52. When I apply, this is pi 1, pi 2 is nothing but this all are is called as a pulsed power supply. Okay. This are pulsed power supply. Okay. Okay. Now we are going to apply. Now when you are going to apply, you think about all 50, 51, 52, everything is same. When you apply everything is same, like when first which circuit will perform, the circuit A will perform, second circuit 2 because the circuit A has to be, next this circuit will get performed. Okay, now we think about if I give at a same time the 50, 51, 52, everything is varying from 0 to VDD. If everything is varying to VDD, what will happen? So this has to produce the output to execute this. Okay, so what will happen during the discharge time, that is meaning when you are going for 0 to VDD, so this circuit is start working. If we say when you go for VDD to 0, then what will happen automatically? So at the by the time this circuit may function, that will affect due to this, because of what happened during this time the capacitor may charge initially, then this will retrace, in the sense when you are going for VDD to 0, what will happen? This will be retraced. That is the meaning of that, right? So now what will happen? There will be a problem. The second stage when it's get execution. So when the first stage when it's going for VDD to 0, so this will try to discharge. If this is gets try to discharge, automatically what will happen? This circuit cannot be energized. There will be some problem will occur over there. So here what will happen? The problem will occur during de-energized time, actually. During de-energized. During de-energized time or during de-energized circuits may be adiabatically energized. So here I can say the gates, inside the gates, right? The gates must be de-energized in the reverse order before the input values to the cascade may change. In this, so here what I said here, thing is here we are having some gates, here also there are some gates, here also some gates are there. So what will happen? The de-energized in reverse order before the input values to the cascade may changes. So that is impractical for several reasons. We cannot able to do before the input values. We cannot do such like that. So what we need to require a large and possible intermediate number of supply voltage waveforms are required, because in single we can, that is the reason we are going for like this 5 0, 5 1, 5 2. In single supply, if I use like say 5 0 only example, only if I use only 5 0 all the places 5 0, what will happen? There will be place. So that is why what we are splitting, that we are having different smaller intermediate supply voltage waveform we are using. But these waveforms all should have the different pulse width, because same pulse width if I am having, we cannot, that means at a time all circuit cannot operational, because when I use cascading in structure, at a time one circuit is finished, it has to give to the next circuit. So that has to be activated, then that has to be activated. If such cases, what you need to use here use different pulse width. Because the reason is I can say because that the n stages requires, if I split into n stages, so n stage cascade requires time is proportional to n. Time is proportional to n to produce each result. Produce each result means I can say the latency is proportional to n and the throughput is universally proportional to n. So now what is the idea here actually? Instead of giving fine out, this is a pulse width power supply. You think pulse width power supply is nothing but piecewise linear, you can say, okay, pulsed power supply. So without the pulse we need to change difference pulse width. So how it can be done? The idea is, one of the idea is we need to design a two-phase non-overlap clock generator. Two-phase non-overlap clock generator. Two-phase, it is different from like two-phase non, in the sense I may get only two inputs. If I want three two-phase sequence there, or four-phase, they'll call like this, four-phase non-overlap clock generator. There's a separate circuit is there. We need to design that circuit. That should be, you have to given as a input, then it will work. Okay. But at the same time, we need to do that. Okay. Next, what I can do in the sense, the latency is this. Okay, it's a proportional, but the throughput, actually, throughput means the number of outputs produces within the fraction of, in the sense, a fraction of time. And it is 1 by n actually. You can see the throughput is getting reduced. The latency is okay. But what about the throughput? The throughput is increases. So how we can improve the throughput? How to improve the throughput? Throughput of the system, I can say. What is the solution I can say? The only solution is use pipeline. Use pipelining system or use pipeline system or pipeline logic, I can say. The technique, pipeline technique actually goes. Use pipeline technique. Okay. What is meant by the pipeline technique? So, or we can say it's kind of like we have to use a latch to hold the input of the retractile stage. So sometimes we can say the conventional latches, what you have to do in the sense, one output we are getting, that has to hold, because initially you can see this point. We mentioned some point here. The adiabatic operation is possible only when if the inputs of every gates are held stable while the gate is energized. So should be held stable. The only thing is what you have to do. You have to use a latch also. We need to hold the value. Okay. So now what we can do in the sense like so we can use a conventional latches. So that is why the pipelining system is how it will be in the sense. Latches you have to use. here. So it will be like this. The pipelining system with general pipelining system, I will draw a general pipelining. It will be like this. This is will be your combination logic. Combination logic A, just A I will say. Okay, this will be your B logic. This will be your C logic. Now what you have to do in between latch. Okay, so now I will connect like this. Then I will get the output here. So these latches are there, is there no? These all are synchronously we have. Then here we have to provide the what? Power supply, that is 5. Right. So now with the respect to the above, the pipeline adiabatic, how the pipeline, in the sense you can see this will be hold value. These all are inputs. So how it will work? First set of inputs are given, it will execute, the output will be stored like this. Okay, see, during the first clock cycle, first set of input will get, so it will be stored in a latch after computation. During the second clock cycle, what will happen? This value will be shifted to over there. This will start to compute. Then by the time even this also will be starts to compute because of the supplying voltage. So like this, keep on the system will work. So as per with our response, so let us draw the our circuit. Let me draw like this. This will be A, this will be B, then this is your input you are applying. For B also you are applying input, then this will be, will take the output. We have the capacitance, then this will be your power supply, that is 5. This logic only, this figure shows that it is a pipeline adiabatic gate. Because here, see, this will be your load capacitance. Okay, so here the load capacitance may be charged through one function network, either through this network or through this network. It may charge, but on a discharge to another network, it is like the load capacitor may be charged through one function network A, maybe this. Okay, next on the discharge, this will be charge. I can say this is charge because one time only one will charge, this will be discharge. Discharge to another B. So the input to the first network must be valid only during the charging phase. So we can make a note. We can make a note. The input to the first network must be valid only during the charge phase. and the preceding phase, that is previous, okay, the preceding phase, the preceding stage can compute new values during the discharge of load capacitance. Discharge of CL. So this is the technique we have to use. So as I mentioned here, there will be two different types of adiabatic. So now what happened? Earlier we constructed the combinational circuits actually. Okay. So now what we have to do in the sense how we can implement for the sequential circuit adiabatic. That is adiabatic sequential circuit. So for sequential circuits, next let us study about the adiabatic sequential circuit. So in this adiabatic sequential circuit actually we are having two things. One is same even here also, fully adiabatic sequential circuit. Then second is partially adiabatic sequential circuit. So now the fully adiabatic sequential circuit fully adiabatic means here the requirements of latches. So let me put that word here requirement of latches. latches to hold the inputs of function network. Arises from need to provide the stable control signal. Through the full charge and discharge. Full charge, discharge cycle of the output capacitance. So compared to the previous diagram, as we shown, 3 stages for the combinational, we split it into small and we see, right? After that I said the pipelining stage. Actually that's pipelining stage only is nothing but for fully adiabatic sequential circuit actually. So here, so example, if you want to control the inputs of energizing path, it's going to be keep stable to handle the de-energizing. So for that, means of the pipelining that does not use latches then exist. And 1 by T scaling by 1 by T is scaling is retained. So here you can see the structure as I mentioned earlier. The previous figure what we drawn in this, let us take that figure. Same figure only we are going to take. This is A, this is your B. Input. This is a 5 means okay. Next here we have the clock signal, that is the load capacitance. This will be your output here and here. The output. This is a pipelining adiabatic, right? So now from this figure you can see. So here we are having to, as I mentioned here, charging path as well as the discharging path also is available actually. Okay, this is charging, this is discharging path also is there. So now in this figure the controlling the input, this one A and B, like this omega various will be there, but here we are not use the latch actually. Here I can see this in this figure we have not, so like the controlling the inputs of the energizing part. This is the energizing part, right? Need not be kept stable actually to energize, to handle the de-energizing. So it means a pipelining that does not use latches can exist, and 1 by T, that is this is for throughput, is that right? 1 by T scaling can be retained. So if the T's get increases, the frequency will be reduces, the operation will be very fast. So there will not be any delay in the operation. Here I can say the control signals of the de-energized part. Which is the control signal here, the input. Control signal means your phi. That is the, I can say control signals. The control signal for the de-energizing part must be stable throughout the discharge to ensure the adiabatic operation. So therefore, we cannot derive directly from the output of the stage A being de-energized. So further what you will do, to energize the de-energizing path must be must instead of be controlled by signal derived from the output of the following stages in the pipeline. This pipeline, a pure copy of the signal is sufficient. But this method will not give the solution because the resources are limited to ability to drive the control signal for the de-energizing path is guaranteed if all the logic blocks, this one, whatever the logic, small logic blocks will be there, all these logic blocks implemented are invertible so that their inputs may be recomputed from the output. So simple we can say, when the de-energizing path is guaranteed, de-energizing path is guaranteed, actually guaranteed when the sense if all logic block blocks implement function that are invertible, means reversible, invertible, so that their inputs may be recomputed. From the output. So it is possible to assemble a fully adiabatic pipeline by constructing all the logic stages like this. It's possible. Fully means all the logic stage has to become in this way, this circuit. Then it is possible to assemble a fully adiabatic. So now we can say from this the complexity of the two mutually inverse function blocks are usually similar, so that the separate discharge path is a factor of 2, not counting the cost associated with the restriction to invertible the functions. So from this we can make an observation that the full or we can say we can make an observation from that. We can say the use of fully adiabatic is only adiabatic solution to very small circuits. Small circuits with the simple functionality. And cases where very slow switching is acceptable. As long as the energy dissipation per transition is low enough. So this is the user. So there will be some limitations will be there in fully adiabatic solution. That is why we need to switch over to the partially adiabatic sequential circuit. Instead of complete, we can go for partial adiabatic circuit. Now let us talk about the partially adiabatic circuit. Partially adiabatic sequential circuits. To take the benefit of adiabatic switching. Without the complications of reversible logic. So we can say the less complex circuitry may compensate for the unfavorable dissipation scaling with the time. So now here what we'll do, let us take an example for a partial adaptive circuit is a simple flip-flop style adiabatic charging logic gate, that is under NAND gate. Okay, first example we are going to take here flip-flop style. So flip-flop style adiabatic charging logic gate. So that examples, this is flip-flop style is nothing but a gate is we are going to implement and NAND function. So let us take how it will be in the sense the latch based on the sense. So latch it is like this actually. Put the first inverter output is AB bar. This inverter output is A, B. Then here I will draw the diagram. The input Input of this gate is AB actually. Okay, the input of this gate is AB. This input is AB bar. Output only will drive this A bar. AB bar. This is the input. Okay, so let us draw in this way. Let me draw the cross-coupled inverter, one cross-coupled inverter. Okay, so two inverters. Okay, so this we are giving the input as V5, that is pulse power supply we are going to give over there. Then here we are going to connect A, B. This will be A, this will be B. Then here this will be the output will be AB bar. Then two inputs, adiabatic logic, right? Here A, B, then here it's supposed to be A bar. Sorry, no, here this series and connection we made in the sense. Then here we have to draw in parallel connection. This is A bar, this is B bar. A bar will be your B bar. Then we have to make it finally all to the ground. This will be your AB. Then the one more connection pending is that is this input, right? So this input will be the output of that. Then this input will be output of this. So here, so we can make it now. This will be your T1, this is T2, T3, T4, T5, T6, T7, T8. So here we can say that T1, T2, T3 and T4. This is cross-coupled inverter pair. This this is the cross coupled inverter pair. Then here A, B input. So this circle which is showing is a flip-flop style actually. It's an AND and NAND function style. So now it is like the functions. This is the function we need to implement with the NMOS logic actually. This is okay. How it will be in the sense this portion is there, no? Here this is the block. It's a NMOS block only. It's a NMOS block only. The functions are F. So that is the output we are getting is like F bar, right? Then here the functions will be like F bar. The functions will be like F bar, okay? Here the functions are F. Because AB bar is output, no? So F bar is equal to AF bar in the sense. Then what about the F double bar? F double bar will be means same thing. Apply the De Morgan's law. What will happen? AB the whole bar will be is equal to A bar. Sorry. So here we will get right. So like a F double bar. F is equal to A bar plus B bar. Correct? F double bar will be is equal to, I will write here. F double bar is equal to AB the whole bar. This will be is equal to A. Apply the De Morgan's theorem here. F bar is equal to AB whole bar, F bar plus B bar. See here, this is the function of F bar, this is the function of F actually. They have written. So now you can see that T1, T2, T3, T4 all are the cross coupled inverter pair actually. So this inverter the input is driving this AB. Now the both inputs and outputs are dual drive. Means the inputs and outputs are dual drive means maybe it's 0 and VDD. Here we are not showing the load capacitance. So the V5, this one, this is the V5 is nothing but a pulsed power supply. This is the pulsed power supply. Now we can see now it has, we can see the first compared to fully adiabatic. The fully adiabatic, what was the count of transistor? The count of transistor was double the static CMOS. That is 2n plus 2n, I think. Correct? Now here, what is we can say? First thing is the device count is low. Correct? The device count is low first. Because there how many transistors was there? When I go for number of inputs varies because we used transmission gate, everything we replaced, right? So for 2 input NAND gate. Now here anything you go, so only thing is this cross coupled inverter will be remain same. Only thing is this block will get changed. So automatically the device count will reduce. So if the device count is reduced, it will approach to the pre-charge dynamic logic. Pre-charged dynamic logic. It is kind of circuit like it's a pre-charged dynamic logic, and the pipelining of these gates can be operated with 4-phase clock. See, here we are going to use the pipelining. Pipeline of these gates can be operated with 4-phase clock. Four-phase clock. It is a relatively simple requirement compared to some other suggestions. Now it is like little bit quite different from the adiabatic amplifier what we described in the previous classes. That is, there is no T gates we use, right? Here see, there is no TGs are used in this. So now this will be a simple flip-flop style. Now we can say in the style it shows a flip-flop gate. As I mentioned, it may consist of two inverters that cross coupled in a flip-flop configuration actually. So as I mentioned earlier here, it consists of two inverters are cross coupled in a flip-flop configuration. In your CMOS VLSI, you might have studied like the latch or flip-flop in CMOS, how you construct it. So that there, if you see, there will be some two inverters will be there. So cross-coupled inverter will be there. That is the same technique here we are using. There is a one. Next here you can see some two pull-down networks. That is PDN. Okay, the two pull-down network, which is used for to implement. This is we used to implement two complementary functions. That is a F and F bar is a two complementary logic function, because we need to get the both the complementary output we have to get. So both the inputs are both the input and outputs are dual rail encoded. Now how the operation will be there here. Okay, let us see the operation. So how the operation will be there? First, what we need to do, so the gate will work as follows. Assume that the load capacitance, which represents the input of other gates and the wiring capacitance, and the supply or clock lines are initially 0 volt, because here we are not specified the load capacitance. So initially all are 0, the supply or clock lines. Okay, so here you may say, where is the clock lines we are giving? This inputs. So clock lines in the sense, it's like your pulse power supply. That is what clock lines actually. Now, all are initially set to 0 volt. The output also, the input of the other gates. Input of the other gates also. Okay. First, we need to provide the set of valid values that will connect exactly one of the output lines to the ground. Since the network will implement a complementary function here, the supply line will be ramped from 0 to VDD, this one, right? The supply line will be ramped from 0 to VDD. So let me apply the value. So let us go for the operation. When I apply, I will apply A and B, both are 0, 0. Okay. When I apply both are 0, 0. This is 0. This is A, B is 0, 0. Then it's a bar. Then supposed to be 1. Even this supposed to be 1. Now you can see initially both are 0, right? This also will be 0 because both are 0, 0. So here we are increasing 0 to VDD. You think about this. Okay. When you are increasing 0 to VDD, it will flow like this. The voltage will flow like this. Now this is 0 in the sense this will be 0, right? This will be 0. Even this also will be 0. Now even here what will be that? AB also will be 0. Then this also will be 0. Now what happened? This transistor T1 is on. the T3 also is on, T2 is off. See, this is on, this is on, this will be off, and this is off. What about here? Here both the transistors are on actually. Here both the transistors are off actually. Correct. So now what happened here when I give, so this value will get passed already. This is on, then your AB bar will get charged. Correct. The AB bar here, what we are having capacitance, just you have to think about that. We don't have the capacitance, so I will get the output because of this. When the VDD flows over there, so that will be charged. This is because of this will be transistors on. When this transistor is on, I will get a charge, means I will get as 1. If it is 1 at that time, what will happen? Both over there, this 1. Or we can go in two ways, right? So even two ways in the sense, you can see even this also will be on in the sense, even this is on, here it is 0, then this VDD will flow over there 1. Right, even here also it will go over 1, here also it will be charged to 1, but you can see here these two transistors are off, there is no discharging path here, but here you can see both the transistors are on, then there is a discharge path over there. When it is charging this in AB, that this I'll get like this, right? So because